Okay, get your notes out, please. All right, we're going to take a look quickly today at something slightly different. We're going to look at some more inequality stuff, and I want to review inequalities in two variables, not just one variable. Like yesterday, we looked at things like this. Right? Like if we wanted to graph, when I say in one variable, if we had something like, let's say, negative 2, I mean, what do we do there?
Subtract 4.
Subtract 4 from everything. Divide by 2, so I'm going to get negative 3. Right? And so if I graph this, there's only one variable there, right? So when we're graphing linear equations that only have one variable, all we need is just the real line, right? So if we were to graph this, it just looks like, what do I do? How do I use those boundaries, negative 3 and 3? Okay, circle there, dot there, and everything in between. Okay, makes sense. Okay, that's what we did in one variable. Now, how does that change if we're talking about two variables? Let's take a look. So what if we've got a linear inequality that involves both x's and y's? So now instead of needing just the x-axis, we're going to need the xy plane. Right? Remember this stuff a little bit? Sort of. Need a little review. Okay, these are all in standard form. We can graph linear inequalities in slope-intercept form also. Okay, so what does it mean to be a solution? Let's talk about this for a second. So just a quick reminder. I know this is not like this is really difficult stuff, but the concepts are important. If I have a line, like let's just say we have the line y equals 2x plus 1. I want to connect the idea of a solution to a graph here. So what's the graph look like? So what do I do if I want to graph this guy? Okay, so there's a point at the y-intercept, and then I just use slope triangle. Good. So if I rise by 2 and I run by 1, I get a second point, and then I can just connect and extend it. I got it, right? Okay, so how many points are on that line? Infinity. Okay, there's 2 shown, but they're an infinite total, right? It's a set of an infinite number of points, and we talked about this the other day. If I just pick a random point in space, like I'm going to pick the point 2, 1. Is that a solution of that equation?
No.
Okay, how come? You're right. How come? Yep.
Oh, I was just listening to David. No, that's because if you plug that into that equation, it won't work.
Okay, if I plug in 2 and 1, right, it doesn't satisfy the equation. I get 1 equals 5, and that's not true, right? So it doesn't satisfy the equation. There's one good reason why we'd say that that is not a solution. Graphically, how could you tell me why it's not a solution? Yes, sir? It's not on the y, right?
It doesn't satisfy the graph.
So it doesn't satisfy the graph either, right? So if it satisfies the equation, then that means it falls on the graph. And those two things obviously have to go together, right? Same thing's true for an inequality. So if it's a solution of a linear inequality, it's just something that's going to make that true, right? So let's look at some examples. For example, if we take the point negative 6, 2, that's a solution of, we got some linear inequality here. Y is greater than or equal to 3x minus 9. If I plug that stuff in, if I plug in 2 for y and negative 6 for x, I get, I think I went too far here. I get a true statement, right? If we were to, I guess they don't do the algebra here, but if I simplify the right side, what do I get? 3 times negative 6 is negative 18 minus 9. Negative 27. Is that a true statement? Okay, so that is one of the infinite examples of a point that satisfies the original inequality, and so it's a solution, right? Okay, so is that a solution? Well, we can plug it in and find out. If I substitute, I end up getting 3, which is not greater than or equal to 5, so that's not a solution, right? It's got to fall outside of the solution set. 4, -1, I checked that one. 5 is greater than or equal to 5, so that is a solution. You get the idea. 2, 1 works out. 7 is greater than or equal to 5, so that's also a solution. So on a line, that was easy enough to graph. We had an end, we had 2 points that we were able to connect and extend, and we created this set that looks like a line of all the solutions, right? All the points that lie on the line are just strung together like beads on a wire. How's that going to work for an inequality? So if we take some examples, and I'm just going to go through this pretty fast. If we just try some points, we're just throwing out a point and seeing if it works. Blue means it works, red means it doesn't, right? So we're trying all these with coordinates, plugging them into this inequality, and I'm trying to make this fast. We had a bunch of examples of ordered pairs that didn't work and a bunch of examples of ordered pairs that did work, okay? What if we just take the line, right? X plus y, instead of being greater than or equal to 1, we just graph the line. Is it a coincidence that that line separates just a few of the infinite examples of the red dots that are non-solutions from a few of the infinite examples of the blue dots that are solutions? No. No, it turns out that line must be the boundary between those two sets, right? Between the area, the region where all the ordered pairs are going to work and the region where all the ordered pairs are not going to work. That make sense? Yeah, I'm going fast through this, but we good? Okay. So we call those in math, we call those half planes, because we've taken a whole plane and we've just cut it in half with a line, right? So one half plane that's divided by this boundary line is going to be the solution set, and the other half plane is not. Okay? And it's always going to work that way for a linear inequality, the two variables. Okay? So what do you think then? What's going to be our strategy if we're given a linear inequality like this? How could, we don't want to sit there and try a bunch of samples. We want to just go right to a solution. What do you think? Okay, so we're going to graph the line, right? The line that's going to separate the two regions. You could put it in slope-intercept form. You don't have to. We could also just leave it in standard form. Either way, we're going to get 2 points and connect and extend and get that line. What do you think we could call that line? The divider. Any other? Well, what do we call a line that separates two regions, like between states? Border, maybe. Like a wall. Okay, we're not going there. Yeah. So in math, we call it a boundary line. Right? It's the boundary between the two regions. Yes, somebody asked. Yes, sir.
Oh, nice question.
Oh, all right. So suggestion. So we're off to a good start. Suggestion is let's start with the boundary line. We don't need to find it just by plotting a bunch of points. Let's just ignore the inequality part of the inequality and graph that line, right? And that line is going to be the boundary between the half plane that's going to be solutions and the non-solution half plane. What else could we do for just a strategy? We want to come up with a procedure. Yes, sir. Okay, so you're going to shade one side of the line. How do you know which side of the line to shade?
Well, according to that, you get tested for.
Okay, so let's try another one. I'm gonna take an example. Okay. Okay, what if we got something like this? What if we've got x minus 2y is greater than 6. Okay, so the suggestion is let's graph the boundary line, right? So the boundary line is just going to be the line x minus 2y equals 6, right? So we could use, we don't have to put this in slope-intercept form. Remember our trick for graphing a line in standard form? We just need 2 points. What would the convenient points be here? Y-intercept and X-intercept, right? So if I want to find the Y-intercept, what do I set equal to 0?
X.
Done. Solve it. -3? Okay, so we get the point. 1 point is going to be the point that if X is 0, we get Y is -3, right? So 0, -3 right there. What about the X-intercept? I set, done, solve it. 6, how about that? So, 1, 2, 3, but that's not very good. I'm a little out of, yeah, they're not very equal, are they? Anyway, so there's my boundary line, okay? There's my boundary line. We might go back and revisit that boundary line if you're having issues with the way I drew that, you're right. We might go back and,
There we go.
okay. Well, that wasn't the issue I was talking about. There might be another issue. But now, which half plane do we shade? So the suggestion is we could test a point, right? So by test a point, does that make sense, right? If we pick a point that's not on the boundary line, what's the easiest one to pick? In this case, the line, it has to be a point that the line doesn't pass through, but the line doesn't go through the origin. So we'll test the point 0, 0. Zeros are easy to substitute, and so if we test that line, if I let X and Y both go to 0, what statement do we get up here? 0 minus 0 is 0 is less than 6, true or false? Or greater than 6, sorry. False. So that means that my test point, is that which half plane is that in, the solution or the non-solution? Non. So the strategy might be that we'll test a point. If it passes, we shade that side. If it doesn't pass the test, we shade away, right? So this is the region that gets shaded, okay? Yes, sir?
When it's just greater than, doesn't the line need?
Okay, good. What about the boundary line, though? In this case, the boundary line is actually not included, is it? Right? Because all we want are the values that of X and Y that produce a number greater than 6, not equal to 6, right? So the boundary line, it's still important because it still divides the two half planes, but we don't include the boundary line this time. And so how would we indicate that? Yeah, we'd have to go back and make the boundary line. Got to make it dashed, right? So if the inequality, does it make sense that if the inequality included an equal sign, then we would actually have, what's that saying? It's saying we're going to get the half plane and include also the boundary line, right? Because the equals would be the equation. So then we would just write the solid boundary line. That makes sense? Okay, I think we can probably speed up this a little bit here. Oops, I don't want to do that. I want to do this. Okay, so our strategy, as you just told me, graph the boundary line, dash line for less than or greater than, solid line if we include equal to, and then to decide which side to shade, test a point. Okay, and that always works. Test a point that's not on the line. Pick the easiest one. What if the line went through the origin? What would we probably pick? Or maybe like 1, 0 or something like that, right? We can have at least 1, 0 in there to substitute. Make it easy. Okay, so what about this one? Let's just look at what these graphs would be. Y is less than -2. What's the boundary line?
Dotted.
It's dotted. Describe the line to me. What
Vertical. No. Or horizontal.
Okay, which one?
Horizontal.
Horizontal. Why? You're right. Why?
It just goes like that.
Okay, how come though? How do I interpret that? If the boundary line, okay, there's no, the boundary line is y equals -2, right? Okay, somebody raise your hand and give me one explanation for why you know immediately that that's a horizontal line. Okay, that's one way, is because if you think about it in slope-intercept form, y equals mx plus b, what's the slope? The x doesn't appear. The slope is 0.
No,
0 is a horizontal line. Good. Okay, what's our other? We had a little trick for remembering real quickly and easily horizontal and vertical lines. If I have only one variable showing up, right? If it's either x equals a number or y equals a number, you know that you name horizontal and vertical lines by their intercepts, right?
Yeah.
Remember that way? So if I get y equals a number, that's just telling me what the y-intercept is, and I've got a line that's always horizontal. Here's another way to think about that. It's the best one of all of them. And this is, for you guys, this is really important. I wouldn't emphasize this much in all the Algebra 2 classes, but if I know that I'm graphing an equation on the xy plane, right? All the ordered pairs would include both x's and y's, right? What does it mean? And this is really actually a very important concept. What does it mean if I take a line that I'm going to graph in the xy plane that doesn't have an x in the equation? What does that imply about values of x?
0.
No.
We're not there.
No. If a variable doesn't show up in the original equation,
Does that mean that all, like, for every x, y is the same result?
yeah, it means that the equation is insensitive to x, meaning it doesn't matter what x you pick. X could be anything. It has no impact on the result. Does that make sense? If x, now I want you to really think about this. This isn't just a point to gloss over. If there were an x in, if there was some dependence on x, right, then the x would have to show up in the equation, right? The math gods need a way to assign a point to, if I pick an x value, they need a way to assign a y value. The only way to do that, if x is important, is to include x in the equation, right? It has to. So if the x doesn't show up, the math gods are telling us, it doesn't matter. Pick whatever x you want. It's unimportant. The only thing that's actually important is y, right? So if x could be anything, but y is always -2, well, what's that tell you? If the y-coordinate is always -2, but the x-coordinate could be anything, that means a horizontal line, doesn't it? Right? Okay. So same thing for this then, right? If we take the boundary line x equals 1, right? If the y doesn't show up, that means that line, the equation is insensitive to y. It makes no difference, right? Y could be anything, take your pick, but x has to be 1. That's a vertical line, isn't it? Right, it goes through the x-axis at 1. And then obviously, okay, if this one's going to be dashed, right? This one's going to be solid. And if this is a pretty easy one to test. And I actually I want you to make some sense of this. So there's the boundary line. Which side am I going to shade? Okay, down. Everybody agree? If y, we're picking all the y values that are less than -2, vertically speaking, doesn't positive mean up, negative means down, right? So this is like you've taken the regular real number line, the x-axis that's sideways, and we just flipped it up like this, right? So values that are going to be less than this, if we were just graphing the y's alone, wouldn't that look like, right? Doesn't that say y is, so we took the original xy plane and we did that to it, right? Or the xy, or the x-axis, right? If we just graphed x is, well, that's bad, isn't it? If we just graphed yesterday, not today, if we graphed x is less than -2, you all would have told me at -2, we're putting an open circle and going to the left, right? Do we agree? We just took that thing and tilted it up, and there it is, right? But the only thing is here, we're graphing on the xy plane, so x could be anything. So we have to take that whole thing and just do that to it. Smear it out sideways, right? I mean, yeah, does that make sense?
And the shaded region is all the numbers that
Do apply, right? Those are all the points where the y value is less than -2. We don't care about the x value. Yes?
In linear inequalities, is there a point where you start graphing in 3 dimensions and all you have to do is add the x and
Sure.
z?
I mean, and so, that's a very good question. It's good to think about this. So we're limiting ourselves to 2 dimensions here, because it's easy to graph, right? I've got it on order, but the special board that I use where I draw in 3 dimensions up here hasn't arrived yet. I ordered from the Acme store, it should be here at some point. That one. We can't do that, right? So we always do 2 dimensions. 3 dimensions, how much harder does it make it? Not really. If I wanted to, so you're up for this. So if I were to graph, there's the XY plane, right? So that's what we call a 2-dimensional space. And so what that really means is 2-dimensional. Now get ready for this. 2-dimensional means that there is exactly room in a plane for 2 lines that are parallel to each other, but that are perpendicular to each other, but that's it. There's no room to put another line on this plane that's perpendicular to these 2, right? Does that make sense? If I add an extra dimension, though, I can't. Now I've got this additional dimension that's coming out of the board, right, into the room. And so now I've got these 3 separate dimensions, but they're all, in calculus we'll say they're mutually orthogonal, which means they're all perpendicular to each of the other ones. So I can draw the right angles. There's a right angle, there's a right angle, and there's a right angle, right? This one's just coming out of the board, right? But can everybody visualize that? Right, so this guy is just coming straight out of the board into the room, and that the dashed tail just means that it's disappearing into the board. Okay? Yes?
Is z coming this way positive or is z going that way?
It's right-hand rule, it's coming this way. Yeah. So what would it look like then if I were to graph in 3 space, which is what we call this? Instead of 2 space, we call this 3 space. What would it look like if we were to graph the inequality y is less than or equal to 2? Well, now instead of just graphing the plane, I would have to fill in this whole volume of space below -2, y equals -2, right? So everything in here like this would all be shaded like with a blue mist, and this would be invisible up here, right? Get the idea? Okay. So does that make it a lot harder? Not really. So why couldn't I do it with 4 dimensions? Mathematically, there's no reason I can't. There's no, I mean, we can do linear equations with arbitrarily many dimensions, right? The only problem is with 4 dimensions, we just can't fit another vector in there. There's no place in our 3-dimensional universe to add an extra direction that's going to also be perpendicular to all 3 of these. To do that, you would need a 4-dimensional space, like a 4-dimensional universe. Do they exist? Not in our universe, but if physicists are correct and the multiverse is real, then they'd be out there somewhere. There'd be 4-dimensional universes where creatures living in 4 space, they would be able to they could say, okay, we can move left and right, front and back, up and down, and blink and blunk. I don't know what they call it. But there's some other directions they could go that would make just as much sense to them. They would say, yeah, that makes sense. Those are all perpendicular directions. We can't see them. We don't have access to look at them. You could never even imagine what it would look like because our universe isn't that way. But is it impossible? No, mathematically it's totally possible. Okay. Anyway, back to reality. If math is reality, exactly. So here's my question to you though. Okay, because I want you guys to be really efficient and good with this stuff. Do we even need to test a point here? We don't really, do we? Right? We can see that on the y-axis, y is less than means down. So we just shade below that line. Similarly, if we graph x is less than or equal to 1, well, there's the vertical solid line that's the boundary. Which side am I graphing, left or right? Left, yeah, right. On the x-axis, less than means to the left, doesn't it? Right? So we don't even have to test a point. You can, but it's overkill. You don't really need to. right? You just know you're shading that side, okay? Okay, so what about, let's do, well, I think we can do both of those. So what about the first one, graph y is less than 2x? Describe the line to me, the boundary line.
Slope of 2.
Slope of 2, y-intercept of 0. So it goes through the origin with a slope of 2, correct? So there's the boundary line. Can you tell me without, I mean, the suggestion here is, and this is kind of, this is a lower level regular algebra 2 thing. Test a point, sure, we could test a point. If we do that, if we try the point 1, 1, which is not on the line, and I plug that in, I end up with the result, does it tell me here? Well, if I plug 1 in, I get 1 is less than 2, which is true, right? So that means I shade that side. Can you think of a way to do this one without shading, or without testing a point? This is a great trick. None of the books talk about this, but this is a great trick. So if I have something, this is in slope-intercept form, right? If the y is isolated, it's in the form y is less than mx plus b. Just focus on that part. Y is less than the boundary means it's going to be what? Below it, right? So you automatically know that if you have an inequality that's in slope-intercept form, you can tell immediately y is less than means you're shading below. Y is greater than means you're shading above. So all I got to do is take this line and just draw straight down to shade it, and you can see which side you're shading.
The y-axis that's past the border.
Say it again.
The y-axis that's past the border line is shaded.
Right. Yeah. And everything else with it. Right. You could take any point on this boundary line, and because you're shading the region that's less than that, where y is less than that, you know that you're shading down from the boundary line. You get my point? Okay. This one over here appears to be a little tougher, right? Because it's not in slope-intercept form. And it's fine. I mean, and you can always test a point. That's fine to do. It always works. It's not that much trouble. But just if you want to be a little bit better at this and see maybe a little quicker way to do it, can you think of a way, just by inspection, we'd say in math, without writing anything down, can you think of a way, once you've graphed the boundary line, to look at this and tell me which way to shade? It's just a finer point. It's not, yes ma'am? You could, exactly. And you don't even have to finish the job. All you need to know is just this part of it, right? All you got to know is it y is less than something or y is greater than something, right? So what would the steps entail? I would get the 2x over here, right? So I get negative 5y is greater than or equal to blah. We don't even care, right? I divide both sides by negative 5, and what's that give me? 5 is less than or equal to, because I'm dividing by a negative, blah. Don't care. All I care about is that part, right? I end up with y is less than or equal to some boundary line. So that means I'm shading down. Y is a vertical thing, right? So, right, but I mean, I want you to always think of it in terms of vertical, because it's a y statement. So we're shading below the boundary line. And then sure, we'd have to go graph the boundary line, but that's no big deal, right? Once we get the boundary line, this is telling me I shade down. And you can do that in your head. You can just look at that and say, okay, it's going to be y is less than down, right? Get the point? Okay. So I want to zip ahead here. Yeah, this is good. Okay, last issue. So what about something like this? How are these things important to us? You know, a lot of times math is used to model stuff. Right, we can have linear functions that predict behavior of some real world thing. Sometimes inequalities make sense. Like this, you have relatives living in both the U.S. and Mexico, you're given a prepaid phone card worth $50. Calls in the U.S. cost $16 per minute. Calls to Mexico cost $44 per minute. So we want to write a linear inequality to represent the number of minutes you can use for calls within the United States and Mexico. And it's going to vary, obviously, isn't it? Like if you used all the money for calls in the US, you're gonna be able to talk for a lot more minutes than if you used all the money to make calls to Mexico, right? But in reality, maybe it's gonna be some mix in between. So how could we represent that? What do you think? Yes, sir. Well, okay. I see where you're going, but let's start a little bit basic here. How could I come up with maybe an expression? Like I'm trying to figure out what are my variables gonna be here?
The money is,
Well, the money is not a variable. The money's actually, those are constants.
yeah.
We know this rate is not gonna change. We know the amount of money is not gonna change, and we know the amount of money here, per minute for both types of calls is fixed. That's not gonna change. But what does change? Time. By time, you mean how many minutes I spend talking to US, calls within the US, and the amount of time I spend calling Mexico, right? So how many variables do I need? 2. Okay, well, let's define our variables then. Probably X and Y. We're gonna pick 2 variables. That makes sense for us mathematically because if we need to look at a graph, we've got the XY plane. So X equals minutes calling US, Y equals minutes calling Mexico, right? Agreed? And we have a total of $50 to spend. Well, how can I come up with then, what I really need here is I need an expression for the amount of money I spend making calls in the US and the amount of money I spend making calls to Mexico, right? And I know that the sum of those two can't exceed 50. Okay, so how would I say, what's my expression for the amount of money I spend making calls within the US? Okay, so say it again. I don't want the 50 in there though. That's really not an issue right now. The 50 is something that's a constraint, but that's not something I'm worried about. I just want to know. All I need to know is if X represents the number of minutes calling within the US and the rate is 16 minutes per minute, what's my expression for the cost for US calls? Say it again. 0.16x. Right? That's the cost for all my US calls for X minutes of US calls, right? How about the cost for calls to Mexico? So combined, that's the total cost. That's the amount of money I'm spending making calls to the US and Mexico. And what's my constraint here? Now the 50 comes into play. There you go, right? Okay, so does it make sense then that okay, we already did this. We're way into these guys. So there's our model. So if we graph it, does that make sense?
Those things that allows for negative minutes, but.
Does it? Because we wouldn't, we would probably limit ourselves. We would say that the domain is going to be only X values between 0 and that number, right? We're going to limit ourselves to quadrant 1. Because even though the mathematical model would extend forever, this is a physical application of a mathematical model, and so we would limit this to where it makes sense, right? So this is fine. If I pick that value right there, I could make 100 minutes of calls to the US and 45 minutes of calls to Mexico, and that's part of the solution. That's possible. But I couldn't do that, right? I couldn't do 100 minutes of calls to the US and 90 minutes to Mexico. I don't have enough money for that, right? Does that make sense? All right. I think we're good. Okay. How much time we got? 5 minutes? Knock yourselves out for 5 minutes. Get questions answered if you have any.